This is a pretty crazy integral. We have to realize something important. Let's say we wanted to solve this integral, 0 to 1 of 2 dx. I think that would be a pretty easy one. We could probably go something like this, 2, 1, and then 2, 0, right? Well, we can follow the same kind of logic if we do something like this. Let's say I wanted to have 2 points in here and 2 points in here. And I took like the derivative of some function, and then I sort of let it go in a couple of different directions. I could say dx, dy, or dz. It's kind of going in multiple directions. So essentially, like, I'm doing the same thing here. I'm finding, like, this is a derivative here, and then I have to integrate that, right? So technically I have the derivative here, and I'm just going to integrate that. Here it was only done in one dimension, in dx. Here we're doing it in 3 different directions. You usually have to parameterize that, okay? But in this case, we're just looking for, like, if this was the derivative, we want the antiderivative. And then we're going to plug in the points that we have. That may seem a little bit strange, but yeah, if you can tell that this is the derivative that you're integrating, if you're integrating the derivative, just find the antiderivative and then plug in the points. All right, so let's go back to this thing that we're doing here. If this was just a derivative, like, we could just put the antiderivative here and then plug in the points, right? Well, if this thing happens to be a conservative field, then we know that's path independent, and we know that that would be the derivative, okay, because the gradient field is conservative, and so you could take the gradient field and find the antiderivative. All right, so how do you find the gradient field? Well, if the curl of f equals 0, then we know that it's a conservative field. Well, the curl in a 2-dimensional field is only going to be 0, 0, and then we have bx minus ay. So let's try to solve that last bit of the curl and see if it equals 0. So bx is going to come from here. And what's the derivative of x here? It's just going to be e to the x cosine of y. And then we're going to want to subtract the ay from over here. And derivative of sine is going to be cosine, so cosine y, and then there's e to the x. Oh, look at that. It turns out that this is equal to 0. Therefore, this is a gradient of something. What's that gradient of? Well, let's imagine we had a f field that was the antiderivative. How would we translate that into something that looked like this? We would have to say fx and then comma fy, right? So essentially we have this thing that's telling us that fx is equal to ex sine of y, this thing, and fy is equal to ex cosine of y. And so if you integrate these things across their respective axes, integrate this thing over x and integrate this thing over y, you should find the antiderivative over here. So let's do that. We'll integrate this in terms of x, and we're going to get e to the x sine of y. And we integrate this in terms of y, and well, lo and behold, we get e to the x sine of y. That is the antiderivative of this. This is a gradient field, and this is the antiderivative. If you took the derivative of this field, of this particular equation, and turned it into a gradient field, you'd get that. So we're just going to take this equation, e to the x sine of y, and we're going to plug it into here. So we basically just go, the first point is -2, 0, and the next one is 9 pi over 2. This is whack, but yeah, this is how you do it. So now we're going to go e to the 9 sine of pi over 2, and then you're going to subtract sine of 0, e to the negative 2, just going to go away. Sine of pi over 2 is 1, so the answer is e to the 9. What?